Today I'm going to talk about electrons. Electrons are the smallest subatomic particle, and we've talked a little bit about the model of the atom and how the model of the atom is changed with our different subatomic particles. And then we've talked a little bit about light, which can be both thought of as energy, like a wave, and a particle, like a photon. So electrons, too, can act as both waves and particles. As a particle, electrons, remember electrons are negatively charged. We usually abbreviate them with a little e to the negative sign, just as a reminder. And that was J.J. Thomson that had discovered the electron. And so he discovered that they have this negative charge and a teeny tiny mass. So the mass of an electron, if we're doing it in our SI unit, which for mass is kilograms, is 9.11 times 10 to the minus 31st kilogram. Okay, so 10 to the minus 31. That's a very, very small number, and it's really hard to conceptualize. So when we think about electrons, we think about them like with the Rutherford model, where we have a nucleus at the center and the electrons are kind of zipping around, or we think about them as an electron cloud. So we kind of visualize these electrons buzzing around the nucleus. So the nucleus has the protons and the neutrons in it. The electrons are somewhere outside of that. And we can picture them as individual particles because they are individual particles. They have a mass, they occupy some sort of volume, even if it's super teeny tiny, but we can also picture them as kind of waves, if you want to think about it that way, or that they have an energy associated with them. And not just energy like I throw a ball and it has kinetic energy because the kinetic energy from my hand and my arm was transferred to the ball, but that electrons themselves are energy. And this is kind of the thing that's kind of hard to wrap your mind around. So they kind of, and again, this model is a little bit antiquated, but the idea of wave-particle duality here, that electrons can have characteristics of both, and that when looking at characteristics of both, we need kind of both of those things in order to describe what an electron actually is, because it's more complicated. And so to do that, one of the ways that we do that is with what is called the Bohr model of the atom. And it's called Bohr after one of the coolest scientists, Niels Bohr. He's Danish. And Niels Bohr was involved in a lot of different things. He was buddies with Albert Einstein even, and kind of bebopping around in the early 1900s. And he was really a physicist, but he was looking at the model of the atom and trying to describe a lot of different things that kind of led to our work with radioactivity and radioactive materials and such. But he was really looking at energy in electrons and kind of the energy from chemical compounds. So Niels Bohr is really cool. Niels Bohr came up with this model of an atom. And you look at this and you say, well, this sort of is simplistic. It looks like a bullseye. That's not what an atom looks like. And remember, there are these two types of models. You can have a model that's a physical model, which actually represents a physical way of thinking about something, or a conceptual model. And so Niels Bohr's model of the atom is that second one, the conceptual type that describes the behavior of a system, not necessarily what it actually looks like. So what you're looking at here, you have your positively charged nucleus, so it has protons and neutrons in it, and radiating out from the positively charged nucleus are these, what he called shells. And these shells represent energy. Or energy levels, if you want to think about it that way. So here's the deal. I have them labeled here n equals 1, n equals 2, n equals 3. This kind of gets into principal quantum numbers, which if you're going on in chemistry will become more important. But for right now, just know that we're kind of going outwards and numbering just 1, 2, 3. And the general pattern is, and kind of think about it in terms of a positive-negative thing. We know that positive charges attract negative charges, and our electrons are negatively charged. So that negative charge likes to be close to the nucleus. So if I have an electron in this shell, or two of them, then these guys are going to be lower energy than these guys in the next shell. So I'm going to draw some electrons in here. Don't worry about the pattern for this yet. We'll talk about them more when we talk about bonding in chemical compounds, but for right now, I just threw some electrons in there just for points of reference. So if I have an electron here in the shell the first shell, n equals 1, then that's lower energy than this one, okay? Because this electron here is further away from the nucleus, so that negative charge is further away from the positive that it wants to be attracted to. And that's our general pattern, that as you move further away from the nucleus, then you have an increasing potential energy. And I'm just going to abbreviate there as PE. So our potential energy increases the further away from the nucleus we get. So if we started to get into outer shells, I only have 3 here, but there are more beyond that. So if I get into shells that are further out from that, they have a greater potential energy. And we care about this. We care about the potential energy of these electrons because the electrons that are in the outermost shells, the ones with the highest potential energy, are going to have the highest potential to do chemistry. They're going to have the highest potential to do chemical bonding, to be gained or lost to form ions, to be gained or lost to do kind of redox reactions. So we get into some other things, and again, I'm just giving you some examples. You don't have to know about that right this second. But for now, we care about the electrons that are in the highermost energy levels, and this gives us a way to conceptualize the energy of electrons, which is important. Okay, so this is kind of the Bohr model of the atom, and this is a conceptual model again. Now there's a couple things about this, and this gets kind of complicated sort of quickly, so we're not going to do a lot of detail on this, but just to let you know. If I was to take this electron here, and I wanted to bump it to a higher energy level, because right, higher energy is more interesting chemically speaking, then I would have to put energy into this system in order to do so. Think about it like this. If I have this pen that's here on the table, it's not going to spontaneously lift itself up, right? It's just going to sit there. It's not going to spontaneously move itself. But if I was to put energy in, so if I put some kinetic energy in, then now I've lifted it up. But it wouldn't have spontaneously done that on its own, right? It normally wants to be here, right? That's the lowest energy possible it can be in this current state. But if I put energy in, I can put it up here. Now if I was to take away the energy from my hand, then what happens is the pen drops back down, right, to its lowest energy state, if you want to think about it that way. The same thing can happen in the Bohr model of the atom. So if I bring in some energy, and I'm going to represent that with just kind of a wave here. So if energy comes in, then it can promote this electron or excite this electron up to a higher level. Okay, and that electron then could go around and move around. It's higher energy, it has more potential to do things, and if it doesn't do anything and this energy source is taken away, then that electron is ultimately going to relax back down to a lower energy state. And when it relaxes back down to the lower energy state, then energy is going to come off. Okay, so we have kind of an energy in here that excites an electron, and that's sort of the terminology that we use. And then it's up in this higher energy level, and then when that electron that's up in a higher energy level relaxes back down, when we take away this energy source, or when it moves away and it no longer feels this energy source, then it will relax back down and energy will be emitted. And that's about the level that I want you to know this at. I mean, we're just kind of talking about this at a very basic, very introductory level, and I just want to note, I want you to note that there's a relationship between energy and the movement of electrons in these different shells, and this is a good way of being able to conceptualize how this energy is working and how these electrons are moving around on an atom, because the way that these electrons are moving around and where they are energetically speaking on an atom are going to influence the type of chemistry that they do. Okay, so there's the Bohr model. Now from the Bohr model, we're going to talk a little bit about what are called atomic orbitals. And this gets to what I was just talking about with our electrons on an atom. Where are they? Okay, and atomic orbitals, I'll give you a definition for it in a second, but what I want to do now is just kind of conceptually to talk about atomic orbitals. So let's, for the purposes of this activity, think about a hydrogen atom. Now hydrogen is number 1 on the periodic table. It's number 1 atomic number, so it means that it has 1 proton in its nucleus, and it's neutral, so you know that it has 1 electron. Now you wouldn't know without any other information about its isotopic configuration or its nuclide symbol, but hydrogen just has the 1 proton, 1 electron in general. It can have other isotopes where there are neutrons, but in a normal, everyday, run-of-the-mill hydrogen atom, it's just 1 proton, 1 electron. So let's model the one hydrogen here. If this is my hydrogen atom, okay, and I have the teeny tiniest of cameras, and this is my proton in the middle here. It's in my nucleus, and I'm taking a picture every just fractions of a fraction of a second, every femtosecond, fractions of a fraction of a second of my 1 electron. Then I'm going to model my 1 electron with just a dot here. So the first picture I take, it's here, and then it's here, and then it's here. And we know that it's always going to be in motion because kinetic molecular theory says that matter is always in motion. And so this 1 electron that I'm modeling, or this 1 electron that I'm taking a number of pictures of, is going to be kind of all over at any given point. But in general, and this is what we would kind of anticipate if we were making a scientific hypothesis, is it's going to mostly want to stick next to the nucleus, right? In general, it likes to be close to the nucleus because that negative charge likes to feel that positive charge. But there's still a probability that it will be somewhere else on the atom at any given point. Okay, so I took a number of pictures and maybe it looks something like this. And now I say, okay, well, this gives me a pretty clear picture of where that electron is at any given time. So if I want to say, where is the electron going to be about 98% of the time, then I could probably draw a boundary in here. And my boundary might look like this. Okay, so that's pretty good. And you can see that there are some times where it's outside of that boundary, but most of the time this boundary encompasses where that electron is. Now, of course, we're in 3 dimensions, not just 2, so I've drawn a z-axis in here to give us kind of some 3-dimensionality. And so when I am visualizing this picture, then think about it as a 3-dimensional camera maybe. So I'm taking pictures of this thing and I can see the 3-dimensional image. And again, all of these are going to be closest to the nucleus. There's some times that I'm going to be outside of these boundaries, but in general these boundaries represent where that electron is most probably going to be found. And we call this boundary, we call this 3-dimensional shape, an atomic orbital. And so sometimes these atomic orbitals are called probability clouds. And so I like to think about them as where the electron will probably be on an atom. And I don't mean probability like, oh, I'm probably going to go to the mall today. I mean in a probability sense. Like there is a 98% chance that you're going to find an electron within these boundaries. So these atomic orbitals give us some very real mathematically driven information of where the electron is going to be. And at its most basic, at its lowest energy, we call this spherical shape an s orbital. And these things are spherical. So just like our hydrogen atom there, our lowest energy orbitals are spherically shaped. Our next highest energy are p orbitals. And the p orbitals have kind of a bow tie or a dumbbell shape or a propeller. And I'll kind of show you a picture of those in a second. D orbitals. D orbitals kind of look like flowers. One of them looks like a p orbital with a hula hoop. They have some wackiness. You can see pictures of them if you just Google them online or in your book. And then f orbitals get even wackier. So in our class we're going to focus on the s and p orbitals, but know that as you increase at a given shell, at a given energy level, this is increasing in energy. So a p orbital is higher energy than an s orbital in the same shell, or a d orbital is higher than a p orbital in the same shell in terms of energy. Okay. So this is just kind of, these are the general pictures of our atomic orbitals. Now each of these orbitals, each orbital, each shape, can hold up to 2 electrons. So each orbital can hold up to 2 electrons. And so within this spherical shape, within this s orbital, in shell 1, let's say, so a 1s orbital, then I can have 2 electrons in it. And it's going to be important in a second. So I said that I was going to draw the p orbitals, so I'm going to do that next. So let me show you what those p orbitals look like, just to give you a sense. Again, you can see better pictures of this than my terrible drawings. P orbitals, again, are kind of bow tie shaped or dumbbell shaped. I've heard propeller also. So if I give myself an XY axis here, a p orbital has a node at the center and 2 lobes. And that's the terminology that we use. The node, again, if we're thinking about waves, the node is where there is the function is equal to 0 or where it crosses the axis. So the node is the place where there are no electrons. So there's that node at the center and 2 lobes. And so this one along the x-axis here could be our px. And again, we live in 3 dimensions, so if this is our y-axis, then we have 2 lobes and a node. There's our py. And if we put a z-axis in here, and we have 2 lobes and a node, then we get something that looks like this. Okay, so here's my 3 p orbitals. There's 3 different configurations or 3 different orientations. I have an x, I have a y, and then I have a z that's kind of coming in and out, or coming in and out if we're picturing this in the camera there. So these p orbitals, again, these are kind of, if we picture them as balloons, as having some 3-dimensionality to them, I usually picture one p orbital as 2 balloons that are held together by their knot. So if you hold 2 balloons together at their knots, then that would give you a balloon out this way and a balloon out this way. That would be one of your orbitals. Now if you have 6 balloons that are held together at their knot, that would give you the shape of all 3 of the p orbitals at a given energy level. Okay, so at any given shell, and again think back to the Bohr model of the atom there, at any given shell we have 3 different p orbitals or 3 different orientations. And so this is the px, the py, and the pz. So if we're thinking about the number of electrons that can be in these orbitals, in one energy level with these 3 orientations, each orbital can hold 2 electrons. So I can have 2, 4, 6 electrons in my p orbitals at any given energy level. And this is going to be important because we can map out the energy of our electrons. And again, the reason that we're doing that, and I'm going to keep coming back to this, is that the energy of the electron gives us information about the type of chemistry that we can do. So, I don't know if you could hear that on this tape or not, but one of my cats just got into a giant box and is now trapped. So I hope that, I guess we'll see how that goes. Okay, so we're going to talk a little bit about energy level diagrams now. So this is relating to the atomic orbitals as well as to the Bohr model of the atom. And so these are called either energy level diagrams or orbital diagrams. And here's how they work. Here's kind of my schematic. I have energy along the y-axis here, so that means that I'm increasing going from the bottom to the top. So my lowest energy orbital is down here, my highest energy is up here, and I increase in energy going up. You could kind of think about this as having the nucleus right here, and then going away from the nucleus, we're increasing in energy, okay, kind of like the Bohr model of the atom. Now a couple different features. The hyphens here represent orbitals. And so each of the hyphens can hold up to 2 electrons. And the way that we represent electrons in this diagram, because that's what we're going to put in it, are with arrows. And you'll see that we put the arrows one up, one down, and this has to do with a characteristic of electrons called spin, which we're not going to get into a lot of detail about. But our electrons here are represented with arrows, and we can put 2 arrows into each orbital. Okay. The other thing that you'll see is the numbers. So 1, 2, 3. So the numbers here give you your energy level or your shell. They relate to the principal energy level, which is the quantum number n if you're in a higher level of chemistry. And then S's and P's refer to the orbital type. So S is spherical, P are your bow ties that we just talked about, etc. Okay, so the way that these work is that we can use what we know from the periodic table, and we talked about how we can relate the periodic table to the number of subatomic particles. We can go to the periodic table and find an element, and we can describe the electrons and their energies based on what we know about that element. So let's, for instance, so I have a periodic table here in front of me. You might want to grab a periodic table too. It's always nice to have one in front of you when you're doing these types of things. And so I look on here and I say, okay, well, let's do aluminum. If I look at aluminum, which is one of our metals, you can see that in the box on the periodic table, then aluminum is number 13, and that 13 is the atomic number, which tells you how many protons are in the nucleus of an atom of aluminum. So we know that we have 13 protons. And we know that atoms are neutral, so in that atom with 13 protons, I also have 13 electrons. Does that make sense? The number of plus signs balance out my number of minus signs. And then it doesn't give me any information about the neutrons because I haven't talked about the isotope. I'm not given the mass number, so I don't know. But for right now, we don't care about the neutrons because we're just focusing on the electrons. So this is kind of the important point. So if I have 13 electrons, then I'm going to put them into my diagram. And I'm going to put them in from the lowest energy to the highest energy. So when I'm filling in these energy level diagrams, I fill them in from the bottom to the top. And I'm going to fill them in until I run out of electrons. So let's put them in here. So here's my first 2. 1, 2, 3, 4. And again, I can only put 2 into each line. 5, 6, 7, 8, 9, 10. Okay, and I'm trying to get to 13, 11, 12, 13. Okay, so what I've done then, great. It's a visual representation with a bunch of arrows. What does it actually mean? Well, it's showing me the energy level of these electrons. So I have some energy, I have some electrons here that are close to the nucleus. This is a pretty low energy situation. So there's 2 here, there's 2 in here. I have 6 in my 2p. I've got 2 in this 3s and 1 in my 3p. So my highest energy electrons are up here in my 3rd shell. And then I have these guys that are all filled in. And so this is all important stuff and becomes more important as you go on. And it will become more important when we talk about bonding. But we can translate this energy level diagram stuff into a quick way of showing or representing the electrons on an atom. So if I translate this energy level diagram into symbols, which are going to look very similar to these symbols here, then I could say I have 1s, 2. So in the 1s orbital, I have 2 electrons. In the 2s orbital, I also have 2. In the 2p orbital, I have 2, 4, 6. In the 3s orbital, I have 2. And in the 3p, I have 1. Okay, so what I've just written then, and this is the way that you'd read it, 1s2, 2s2, 2p6, 3s2, 3p1. This is called an electron configuration. And the electron configuration is a quick way to figure out the energy levels of our different electrons. We can see at a glance that the highest energy ones are in the third shell, and there's 3 of them between the 2 types of orbitals. Okay, and we'll talk about again why that's important later on. So a quick way, if you're given an electron configuration to determine your element type, is just to add up all these superscripts. The superscripts tell you the number of electrons in those orbitals. So if I have 2, 4, 10, 12, 13 electrons, if I go to my periodic table, then I'd say if I have 13 electrons, then if I'm talking about a neutral atom, which I'm not given any indication that I'm not, then that would be aluminum with my 13 protons. So this is that electron configuration. And on some periodic tables you will see the electron configuration written in the box with the element. It's that important. So let's do a couple other examples of those electron configurations. If I give you one that looks like this, and said, what element is this? Then you would go to your periodic table, and again, you'd break one out, and you'd say, all right, well, what do I need to know? How am I going to use this? So I have 1s2, 2s2, 2p6. All right. So my highest energy electrons are in my second shell. Okay, and there's 8 of them in the highest level. All right. So you add up your superscripts, 2, 4, 10. So that means that you have 10 electrons total, which means that if we're looking at our periodic table, the one that corresponds with 10 electrons is over here in our noble gas column, and it is neon. Now again, in our level, I'm only going to give you electron configurations with S's and P's, so we're going to be somewhat limited by the electron configurations that we're giving, because we're just easing our way into these. And so we're not going to do this in a lot of detail, but I just wanted you to recognize that. So let's do another one more. All right, so you're looking at your periodic table, and I say, what element is that? And so you say, okay, well, let's count up our superscripts. I have 2 in the 1s, 2 in the 2s, that's 6 in the 2p, so that's 10 total, 12, 17. So that gives me 17 electrons total. So I go to the periodic table. Number 17 on the periodic table is Cl, which is chlorine. Okay? And this is going to be the level that I want you guys to know it. I'm not going to have you give me one. If I give you a name, you're not going to give me the electron configuration. It'll always be the other way around. I'll always be giving you something like this, and you'll have to interpret it. So the goal is to be able to interpret these electron configurations and then tell me the identity of the element. So it's important then to understand what you're looking at, what all the different symbols mean, how it relates back to our different things like the energy level diagram, so how it relates to these types of things, going from this to an electron configuration, and then also how it relates back to the Bohr model of the atom, which says that we have these electrons that are in shells, and so here's my 1s2, and then I have 8 in my shell, so that would be 2s2, 2p6, right? And so we can talk about how this is all related, and this will all come together a little bit more when we talk about the Lewis dot models and we talk about bonding in a little more detail. Okay, so that's just a quick little introduction that finishes off our chapter 4, which is all about the model of the atom and a little more about electrons. And if you have any questions, as always, please don't hesitate to let me know.